Today we are going to talk about amplifier circuits in general, and we are going to lead towards a discussion on operational amplifiers. So this lecture will be entitled Introduction to Amplifier Circuits. Before we begin this lecture, I want to talk a little bit about what we covered on amplifiers, specifically op amps in circuits 1, where we had some ideal op amp rules that we found that we could apply. Those ideal op amp rules are actually only valid when we have what's called negative feedback, which we'll talk about in this class in a moment. And even then, it's actually only very certain and specific conditions. We are going to start talking about amplifiers in a general sense, then talk about what are called open loop configurations, then positive feedback configurations, and then finally negative feedback configurations. So it's going to be the better part of a week and a half-ish until we can actually apply those ideal op amp rules once we understand when and why they are actually valid. So I'm just giving you this kind of speech as a precursor because we are not going to be able to make the assumptions that the voltage is present at the inverting and non-inverting terminals are the same, and we can't make the assumption that no current flows into or out of the input terminals until we actually get to negative feedback amplifiers. All right, so let's say that we have a time varying waveform. And I'll do this in red. And let's say that it's a simple sinusoidal signal. And this signal could represent a voltage waveform, a current waveform, or even a power waveform, right? Because we know for a sinusoidal voltage or current signal, the power being delivered to an arbitrary load should also be sinusoidal. Well, if we want to transform that signal into the following waveform, I'll do this in blue. Where this blue waveform could additionally represent a voltage, current, or power. We have two options to perform this operation, okay? What I am trying to graphically depict here is that we have a time varying waveform. And our goal is to make this time varying waveform a scaled version of the input signal, right? So we want a system where we can input a small signal, and at the output, we see a large signal, maintaining the characteristics of our input. There are actually two options to carry out this operation. The first involves amplifiers. And the second involves transformers or magnetically coupled circuits. Okay. So I want to talk about the fundamental differences between these two different means to effectively get roughly the same goal. All right. And we're going to talk about these distinctions because they really lead to two very disparate applications, right? So in an amplifier circuit, these are typically active devices. Can anybody tell me what I mean by an active device? Bradley. Yes, stated it a little oddly, but yes. So what I mean by that is an active device requires external power to operate correctly. Okay. A transformer is a passive device. Which means it does not require any external power in order to operate. So like resistors, capacitors, inductors are all examples of passive devices because they exhibit resistance, inductance, and capacitance, regardless of whether or not they're actually connected to anything else. Whereas a circuit like an op-amp doesn't amplify a signal unless you actually connect it to a power supply to make that happen, okay? So that's one fundamental difference. Another is the output power relationships. So because an amplifier is an active device, that means the power delivered by the amplifier, P out, does not have to be the same as the power of the input signal that's applied. We can draw extra power for our output signal from those external power supply connections. All right, this is a really big deal with regards to amplifiers. For a transformer, because it's a passive device, the output power is required to be less than or equal to the input power. So in an ideal case, the input power and the output power are the same, but for a real transformer, there will be some losses that occur so that every transformer stage you have to either boost a signal or attenuate or buck a signal has some associated losses, which means the amount of power that's delivered through each stage gradually decreases. We won't see that in an amplifier. So from this, we can define really what an amplifier does. An amplifier is a circuit or device which increases the magnitude of the signal applied at its input. So for a generic black box amplifier, where On the left-hand side, we will have input terminals across which an input signal X of t will be applied, where X of t can be a voltage, current, or power. On the output side, or on the right-hand side, we take our output, which again can be a voltage, current, or power. Our amplifier circuit has a transfer function, so a relationship between the output signal and the input signal that is defined as A is equal to Y of t divided by X of t. So this transfer function A depicts how the amplifier circuit operates on the input signal to generate the output signal. And in general, we can say that Y of t is simply A times X of t, where A, for the most part, is going to be a scalar amplification factor that's more commonly referred to as the gain of the system. Now, in later classes and even later on in this class, we'll find that sometimes A isn't necessarily a constant. It can have frequency dependencies and all that kind of stuff, and be effectively have some values at particular frequencies and other values at other frequencies, which we will use to develop the rationale for filters and things like that. But for the next several lectures, let's consider this constant, or this value A, to have a constant value, just to make our life a little easier. Okay. So the next thing that I want to do is to walk you through the 4 basic amplifier types. Excuse me, 5 basic amplifier types. All right, classified by their input signal and output signal. I'm just going to draw a simple table here. Input, output, and name. So if we apply a voltage signal at the input and we measure a voltage signal at the output, unsurprisingly, we call this a voltage amplifier. Right? If we apply a current signal at the input, measure a current signal at the output, and we have a current amplifier. If we apply a voltage signal and measure a current signal at the output, we have a transconductance amplifier. If we apply a current signal and measure a voltage signal, we have a transresistance amplifier. And finally, if we input a power signal and measure an output power signal, we have a power amplifier. You all may not be aware of this, but you deal with these types of amplifiers on a daily basis. Okay. So let's say you're driving in your car and you're listening to the radio. Okay. The mechanism by which the signal is received by your antenna and convert it into a signal that you can actually hear involves the use of voltage amplifiers, transconductance amplifiers, or that's your signal processing portion, and then driving the speaker so that you can actually audibly hear the signal is carried out by power amplifiers. Your cell phone, the radios and various functionalities, literally use all of these in some shape or form, okay? So we're dealing with these amplifiers literally anytime we have any sort of analog signal processing. We are largely going to devote our time looking at voltage amplifiers in this class. When we get on to electronic circuits, which is in your junior classes, that's where we'll start taking a look at current amplifiers, transconductance amplifiers, and transresistance amplifiers. And then when we wrap up those, we'll introduce the concept of power amplifiers as Class A, Class B, Class AB, and Class D amplifiers when we're designing power electronics in our later courses. So let's look at a simple voltage amplifier circuit, or a representation of a simple voltage amplifier circuit. Here in the middle will be our amplifier. And I'm going to call the voltage across the input terminals Vn of t, because I'm very unimaginative. And I'm going to call the voltage present across the output terminals the out of t. But we're going to expand this system ever so slightly. Let's say that we have a practical voltage source Vs of t, which may have some internal resistance, R sub s, supplying our input signal. And let's say that our amplifier is driving a load, which we'll call R sub L, which has an associated voltage dl of t like so, so that we can subdivide this system into three distinct portions. On the left-hand side, we have our source. In the middle, we have our amplifier. And on the right-hand side, we have our load. This is what the practical application of an amplifier circuit would look like, where we don't really know or care what our amplifier circuit actually is just yet. Okay. What is the ideal behavior of this system? It's not a trick question. What's the purpose of the amplifier? It's to make this signal, VL of t, be a scaled version of Vs of t, right? So ideally, VL of t will be A times Vs of t, where A is representing the voltage gain of our amplifier circuit. Okay. So what we're going to do, based on this ideal condition here, is develop a generic model for amplifier circuits. Okay. So if we looked in to the input terminals here and here, looked into the amplifier, what does Thevenin's theorem tell us that we'll see? Don't know why you guys are laughing. So we're applying Thevenin's theorem. We're trying to find the Thevenin equivalent of everything to the right of this pair of terms. What does Thevenin's theorem allow us to do? Exactly right. So Thevenin's theorem says that we can convert any linear two-terminal network into a voltage source in series with a resistance, right? So we are going to see a dependent voltage source, and I'll explain why, in series with some resistance, okay? We see a dependent voltage source because we know that the output voltage is coupled to whatever the input voltage is, right? It has, we're looking for a scaled version. So we have a dependency on that input voltage. So on the right-hand side of our model, actually, I misstated that. Okay, so let's try this again. Screwed that up. All right, when we're looking in, my apologies. When we're looking in here, we only see a resistance, actually. The reason for that is we are disconnecting everything over here to the left and looking in. So we simply see a resistance when we're looking in. When we look in through the output, that's where we see the voltage source in series because we're looking at a live network. So my apologies for messing that up. In short, what our model should look like is this guy, where we have an input resistance, and then on this side, we have what's called an output resistance, which is just the Thevenin resistance seen when we're looking into the output terminals. And then here, we have A times Vn, where this voltage is Vn, and this voltage is Vout. This is what's called a practical op-amp model. Just for the sake of argument here, I'm going to connect it to the remainder of our circuitry. Like so. And I'm going to put a nice little box around it. All right. Any amplifier can be characterized by this model, regardless of what its internal circuitry is, or this model or a modified version of this model. Okay? Now, an operational amplifier, which is what we're actually going to be talking about here for the next bit, is a specialized version of this because it has what's known as a differential input. So instead of being able to take a single input signal, it can take two different input signals and do mathematical operations on those. So our practical op-amp model is thus this guy that I'm about to draw. So here we have our input resistance. I'm arbitrarily going to say that the top terminal is our non-inverting input, so it's corresponding to the plus sign. Our bottom terminal here is our inverting input terminal. And so that makes the voltage drop across Rn what we're going to call VD, where VD stands for differential voltage, because it is literally the difference between the voltages applied at these pins. On the other side of our circuit, the output side, we're going to have our dependent voltage source, where our voltage gain, AVOL, which stands for open loop voltage gain, so this is kind of the inherent gain of the op amp, gets multiplied by our differential voltage VD. And then we have our resistance R out, like so. And all of these voltages are measured with respect to a common ground. So they are all considered to be nodal voltages. So this model is how we are going to represent our op amp for the next several class periods. Now, you may be saying to yourself, this seems a little complicated. You're not entirely wrong, but I would like to show you what the internal circuitry of an op amp actually looks like. Find where I have it saved up here in Dropbox. So this is the data sheet for a Texas Instruments MUA 741 general purpose amplifier. I believe on page 7. Nope, maybe it's 9. Here we go, 10. And I'm probably going to need to make this a little smaller. Well, it's being difficult for whatever reason. There we go. This is a simplified version of the internal circuitry of one of the oldest and most simple op amp designs. Contains 22 transistors, all of them happen to be bipolar junction transistors, 11 resistors, a single diode, and a single capacitor. Okay. This is a simple op amp, all right? Analyzing this guy is a nightmare using this, okay? On the data sheet, though, the information that we are given, and this big wall of text here, the electrical characteristics, includes things like our open loop gain, our output resistance, and our input resistance. So we can model any practical op amp just using those 3 simple parameters. So there is a significant limitation to this model that we are about to explore in this example problem here, okay? So let's say that I have the following circuit. Here's my non-inverting input terminal. Here's my inverting input terminal. Here's my output terminal. And I'm going to explicitly draw power supply terminals as well. So in this class, we're going to, the power supply terminals are going to be extraordinarily important. So I'm usually going to tell you what those voltages are. And they were largely ignored when we did circuits 1, except for the lab. So let's say that I have a power supply voltage of VCC plus is equal to 10 volts on the positive power supply terminal, negative 10 volts on the negative power supply terminal. Let's apply 1 volt to the non-inverting input. And let's ground the inverting input terminal. And lastly, all we're trying to figure out is our voltage V out. Now, a practical op amp is characterized by its open loop gain, AVOL, its input resistance, RN, and its output resistance, RN. So let's talk about the open loop gain first. Okay. Most general purpose op amps have an open loop gain of somewhere between 10,000 and 10 million. Okay. For this example, let's split the difference and say that we have an open loop gain of 100,000 volts per volt. The input resistance of an op amp largely depends on the transistor technology that's used in its construction. For bipolar junction-based op amps, the input resistance is usually on the order of mega ohms, so 10 to the 6 ohms. For MOSFET-based operational amplifiers, the input resistance is usually on the order of tera ohms, or 10 to the 12 ohms. So it's literally 1,000,000 times larger. And that's due to the internal capacitance of a MOSFET transistor. So let's say that we're dealing with a BJT-based technology. So we're going to be dealing with a modest 1 mega ohm of input resistance. And lastly, the output resistance. So that depends on the different types of amplifier stages that are used to get the operational amplifier performance. Typically speaking, the output resistance needs to be as small as possible. It's usually on the order of 1 ohm or less. Let's say this one was designed particularly poorly. And so our output resistance is 25 mega ohms, or excuse me, 25 ohms. Okay. So what I would like us to do is to determine the output voltage for this configuration, where our output voltage here is an open circuit voltage. All right, so the first thing that I'm going to do is redraw my circuit using my practical op amp model. So I start with just the simple model. This is V plus, this is V minus. I'll put the value of Rn in momentarily. All right, so first things first here, VD, my differential voltage, is literally always going to be the voltage measured at the non-inverting input terminal minus the voltage at the inverting input terminal. So it's always going to be V plus minus V minus. All right. My Rn value is 1 mega ohm, so I'll just put that here. My R out value is 25 ohms. My voltage gain is 10 to the 5 times VD. So my inverting input terminal is shorted to ground. So I'm going to draw that by connecting a wire directly from my inverting input terminal to that bottom ground rail. My non-inverting input terminal has a 1 volt voltage applied to it, measured with respect to ground. So I'm going to put a 1 volt source here. My output voltage is an open circuit voltage. So here is the out. Is everybody okay with the way that I've redrawn this circuit using the practical op-amp model? So the 1 volt source is because I have 1 volt with respect to ground applied at the non-inverting input terminal. So this node right here represents the non-inverting input terminal. This node is ground, and there's a 1 volt potential difference between those two spots. Any other questions about how I've redrawn this? Bradley?
Do a 10 volt and negative 10 volt power supply.
Fantastic question. So that's one of the limitations of this model, is that there is no mention whatsoever of the power supply voltage. So let's calculate the output voltage and then we'll circle back around to that question, okay? So by inspection, what is our differential voltage VD? 1 volt, right? Because it's 1 volt minus 0 volts is 1 volt. What is our output voltage? A 100,000 volts, exactly right, because there's no current that's flowing through this 25 ohm resistor since we're looking at an open circuit voltage. So since there's no current flowing through the 25 ohm resistor, V out is exactly equal to 10 to the 5 times VD. So supposedly, V out is 100,000 volts. I see a lot of crinkled up faces going, how the hell is this possible? And the short answer is it absolutely isn't. You're right to be very suspicious, okay? So this is the limitation of our model. A practical op-amp, the output voltage cannot be more positive than the positive power supply voltage or more negative than the negative power supply voltage. So our output signal is actually constrained to be between positive 10 volts and negative 10 volts. Technically, this is only true for what are called rail-to-rail op-amps. Most op-amps aren't rail-to-rail, meaning that the range of output voltages is actually a little bit smaller. But for the sake of simplicity for this class, we are going to consider all op-amps to be rail-to-rail, so that our output voltage is always constrained to be between VCC plus, the positive power supply voltage, and VCC minus. This is bringing me into our next topic, which is called saturation distortion, okay? So in a real op-amp, output voltage cannot exceed power supply voltages. So we can define our output voltage as a piecewise function. Okay. So I'm generically writing this specifically for this example problem that we just worked. We will see that V out is VCC plus, which is 10 volts, when AVOL times VD is greater than or equal to VCC plus. It will be the actual value of AVOL VD when, VCC minus is less than AVOL times VD is less than VCC plus. And lastly, it will be VCC minus, which is negative 10 volts, when AVOL times VD is less than or equal to VCC minus. These particular ranges have names. Okay. So whenever the output voltage is the positive power supply voltage, we call this positive saturation, where saturation in this case means that an increase in the input voltage does not cause a corresponding increase in the output voltage. So we say that the output is saturated because it's no longer changing. Similarly, when the output is pinned at VCC minus, we have negative saturation. Because a decrease in the input voltage does not give us a corresponding decrease in the output voltage. And then finally, that middle section is where we have linear operation. So our model behaves exactly like it's supposed to under linear operation, and that should kind of make sense because our model is based on Thevenin's theorem, which says any linear two-terminal network can be replaced by a voltage source in series with a resistance, right? So our linear model is applicable when our device is behaving linearly, and it gets thrown away when our device isn't. Bradley.
Our VD was greater than our power supply, our VCC plus.
So if VD were larger, AVOL times VD, right, so it's all dependent on what the differential voltage is. So differential voltage can absolutely be larger than the power supply voltages because you can physically connect that way. The output is always going to be constrained to be between VCC plus and VCC minus. Okay. So our last topic for today, before we play around with LT Spice a little bit, is what's going to be called the linear range of an amplifier. Okay. So effectively, we need to know what input voltages correspond to this region of operation. So where is our amplifier actually behaving like an amplifier instead of just giving us a saturated output? All right. So the linear range is pretty simple. It it will be just VCC minus divided by AVOL is less than VD is less than VCC plus divided by our open loop gain, right? So effectively, we are going to see for these open loop configurations a very small linear range, right? If we plug in our values here, that's going to be negative 10 volts divided by 10 to the 5 volts per volt is less than VD is less than positive 10 volts over 10 to the 5 volts per volt, or negative 100 microvolts to positive 100 microvolts. Okay. That's the input voltage range over which our amplifier is behaving linearly. That is incredibly small, right? The open loop configuration, like we've detailed here, is not used in a whole hell of a lot of applications. It does have very specific applications, which we are going to introduce on Monday, but largely we use feedback as a means by which to extend this linear range. Yes, sir. So effectively, yes. Let me explain exactly what I mean by that. We can tell that this is nonlinear because our output voltage is beyond our supply voltage, right? So in this particular instance with a VD of 1 volt, you are 100% correct that our amplifier is behaving non-linearly, which means our output is either in positive saturation or negative saturation. And we can see that it's positively saturated because 100,000 volts is much greater than our VCC of 10 volts. So in truth, our output voltage should only be 10 volts. So let me find my mouse real quick. And then we're going to just play around with LT Spice for a moment because I want to show you guys a couple of things. All right. And my keyboard is going to be useful. So if you open up the select component window here, you'll see in this left-hand column, op amps in brackets. What that means is that there is a folder full of op amp models. So if I click on that, there are literally hundreds of different op amp models here. Okay. Now, this software was written by a company called Linear Technologies, which is why it's LT Spice. And so inside for free is the simulation model for every Linear Technologies op amp that they produced before they were bought by a company called Analog Devices. Over to the left, all of these op amps that start with AD are analog device op amps. Okay. Now, they haven't been bought by anybody else, at least not yet to my knowledge. So on semiconductor op amps, Texas Instrument op amps, all that kind of good stuff, they aren't in here natively. But if you went to, say, ti.com and looked for a specific op amp, usually somewhere where you can find the data sheet, they will actually also include the SPICE model as well, so that you can import the characteristics of their op amps and other microelectronic circuits for use in your simulation. Now that can be a bit of a pain in the ass trying to hunt down a SPICE model for a particular thing. So what I'm going to do is I'm going to scroll all the way here to the right. And look at this guy right here. This is Universal Op Amp 2. It is a universal op amp model that allows 4 different levels of simulation accuracy. And then it says, see this file path for details. Okay. I'm going to click on this. And by the way, you can just get this directly from the component menu by typing UNI, and it'll pull up this by itself. Here's our universal op amp. I've just placed it here. When I right click it, I want to talk you guys through a couple of different things. Okay. This SPICE model right here is critically important. Connor.
I've got it as an option. My description isn't the same.
You've probably updated LT SPICE in the last 3 years, and I haven't.
Okay.
That's probably why. If it's universal op amp, it's going to behave the same way. Yeah. So the SPICE model here is critically important, or the SPICE level. So if you right click it, it should pull up a drop down menu. So let me explain what the different levels are. Level 1 treats it as an ideal op amp in every way, shape, or form. Okay. Level 2 treats it like an ideal op amp, except that the output is constrained to be between the power supply voltages. Huh.
We also have level 3, level 1, and level 3 has other op amps. So like universal op amp 3.
Oh, okay. Well, then apparently I need to update. Well, what I was going to say, we're going to use level 2 in this class anyway, okay, for the overwhelming majority of stuff. Apparently, I will need to update LT SPICE after 3 years finally. But the other levels, which I guess correspond to other op amps for you guys, have editable parameters. So right here, the first thing that we could edit is AVOL, the open loop gain. So it's set to 1 meg, which means 1 million. Okay. Then we have what's called GBW, the gain bandwidth product. So this is having to do with the frequency response of an op amp. We're not going to really deal with that in this class, but you're literally going to be measuring things like that when you do the labs for circuit 3 and all that kind of good stuff. Then there are things called the slew rate. Slew rate is effectively just a measure of how quickly the output of the op amp can respond to a time varying input signal without causing any distortion. So effectively, you could find a data sheet for an op amp, change these parameters to match the op amp that you're interested in, and not have to go hunt down an actual coded out SPICE model if you were so inclined. Okay. For the purposes of this class, though, we're just going to largely leave it as level 2, in as much as we will have an ideal op amp where the power supply voltages will constrain our output signal. Okay. So let's leave that like so. All right. Now, a couple of odd things here. For whatever reason, the positive power supply voltage terminal is next to the inverting input terminal, and the negative power supply voltage terminal is next to the non-inverting input terminal. Couldn't tell you why they have it set up that way, but it just is. So the one with the plus sign that's sticking up is where you put your positive power supply voltage. The one with the minus sign that's sticking out in this way is where you put your negative supply voltage. Then here we have our inverting input terminal, and here we have our non-inverting input terminal. So what I'm going to do is to show you how I like to set up op-amp circuits so that we don't have a bunch of sources all over the place that overly complicate our circuitry. So I do that. I'm going to put a voltage source here, way on the left-hand side. I'm going to put another voltage source here. I'm going to rotate it twice so that the positive polarity is on bottom, and I'm going to put it underneath. And then what I'm going to do is I'm going to tie those two negative polarity terminals together. And then I'm going to give myself a little stub of wire. And that's where I'm going to put my ground. So let's match the example that we had a moment ago. I'm going to say that my positive supply voltage is 10 volts. My negative supply voltage is negative 10 volts. I did that by just right-clicking in the middle of the voltage source and then giving it a value. And then here's the thing that I think is nifty. Okay. So if I use that label net button, I'm going to just type in VCC plus. And what I've done here is I've said that the positive terminal of this voltage source is now node VCC plus. Well, if I apply that label over here to the positive power supply terminal, this puts 10 volts here without having to wire it directly to that voltage source. I can do the same thing for VCC minus. So now I've applied my negative power supply voltage to my negative power supply terminal. For this particular op amp, I believe the inverting input terminal was grounded. So I'm just going to put that here, except that I messed it up slightly. And I'm going to give myself a little stub of wire here and a little stub of wire here. And I'm going to give myself another voltage source. And we're going to play around with some things here real quick, okay? So in our example, it was a simple 1 volt source. Let's no longer have a 1 volt source. Let's make it a sine wave. Okay. Let's make it a sine wave that has no DC offset, so we can either put 0 or leave the first spot blank. Let's give it an amplitude of 2 volts. And let's give it a frequency of 1 hertz, just so it'll make it really easy to see how long we want to run our analysis cover. Because I don't want to. Okay. That's it. Yeah. So I'm just saying it's a pure sinusoidal wave that's not level shifted one way or the other. Again, I'm giving it an arbitrary amplitude of 2 volts and a frequency of 1 hertz. So that's 1 cycle per second, so that if I want to look at 5 cycles, I know to just put in 5 seconds as the transient analysis time, something like that. I'm going to make the bottom terminal of this ground. And then I'm going to label this guy VN. And then put VN on the non-inverting input pin. And then lastly, just for the sake of argument, I'm going to label the output pin Vout. So I do this so that all of my supplies and all that kind of stuff aren't mucking up the behavior of the circuit. You don't have to do it this way by any stretch of the imagination. I just prefer to do it this way because it's pretty clean looking. Okay. So I'm going to edit my simulation command and let's just have it be for 3 seconds so that we get 3 cycles. And then I'm going to run. And what I'm going to do is plot Vn. So we see that we have a sinusoid going from 0 up to 2 and down to -2 over and over and over again. By the way, some of you guys probably have a black background here as opposed to a white background. If you want to change the colors of things, if you go to Tools and then go to Color Preferences, if you literally go to Waveform and click on the background, you can then edit the background color. If you click on V1, that lets you change the color of the first signal that you look at. If you click on V2, that lets you change the color of the second signal, and so forth and so forth. If you click on the grid lines, you can change the color of the grid lines. Everything is customized. I like to use a white background because when I print these out, it doesn't waste a ton of ink and you can actually see things.
With analysis or simulation.
Transient.
Stop time.
Yes. Yes.
How did you change this?
Okay, so I went to Tools and then Color Preferences. And so you can change the colors on your schematic. So you can also change, not really the font, but you can make things like boldface and all that kind of stuff as well. And then for your plots, click on the waveform option, and then you can change all your colors there. All right. No problem. So let's cancel that. So that's my input. Now I click on my output. I'm plotting my input and my output on the same graph. And so effectively, what we've got here, because we're using Spice Level 2, we've taken a sinusoid and we've converted it to a square wave by using an open loop Opamp, where the peak values of the square wave are determined by what our power supply voltages are.
And you do not need a resistor supply because the current motor is operating anyways, it's just operating off.
So there is going to be some current, but it's going to be incredibly small, right? So if we are putting a 2-volt signal, that 2-volt signal is effectively being applied over a resistor on the mega ohm scale, which means that it's drawing microamps of current if it's a BJT related device, or picoamps of current if it's a MOSFET related device. So not enough to really matter.
So the resistance in the op-amp is all that's needed.
Exactly right. Yeah. If we had left this at Spice Level 1, LT Spice would kind of freak out because it would just be applying effectively an infinitely large gain to this sinusoid, right? So it would
be an error.
I'm honestly not sure. Let's find out. So it's capping the output at 2 megavolts. So it's capping it at a gain of 1 million, but it's not including any power supply issues. Okay. Obviously, that's very unrealistic. Yeah. And then because of the scale, it looks practically like all right. So I just wanted to introduce you guys to kind of how I like to lay out op-amp circuits and all that kind of good stuff, because we're going to be simulating an awful lot of them over the next several days and all that kind of good stuff. I think this is a good stopping point for today. On Monday, we are going to look at, I guess, more formal applications of open loop op-amp configurations. So we're going to introduce the concept of inverting and non-inverting comparators. We're actually going to design a circuit for a specific function. And then we're going to talk about resistor biasing of these open loop op-amp circuits as well. But that's enough out of me for today.